More on dummy variables. We use dummy variables to shift the y-intercept. It doesn't change the other linear terms. So, for example, consider a regression that wage is beta naught plus beta 1 age plus beta 3 times some dummy variable d plus the error term. For people who have that dummy variable equal to 0, their wage is beta naught plus beta 1 age. The other people for whom d equals 1 are going to see parentheses beta naught plus beta 3, close parenthesis, that'll be their intercept, plus beta 1 age. So it's just shifting the intercept. But what if we want to change the slope on age? What if people with that dummy variable equal to 1 accumulate experience different, or accumulate the rewards to experience differently? Perhaps we think that delta wage, delta age should be different between the groups. Now, this model does not require it to be different. It allows it to possibly be different. To accomplish this, we add some interaction terms. We interact the dummy variable d with the age variable. And by interact, I mean nothing more than the simple mathematical operation of multiplying the two together. We create age times d. Why? Well, if we break that down into two segments, we can see what's going on. For people who have d equal to 0, the base group, they'll still have the same regression, beta naught plus beta 1 age, plus some error. But the other group are going to have beta naught plus beta 3, so they're going to start with a different y-intercept term, but then the coefficient on age will be beta 1 plus beta 4, in parentheses together, multiplied times age. People in group 0 have delta wage, delta age equal to beta 1. But for people in group 1 with d equal to 1, they're going to have delta wage, delta age equal to beta 1 plus beta 4. Again, this is not a requirement. The regression could estimate the beta 4 is 0, meaning there's no perceptible difference. If you work through the mathematics, you can rewrite the equations a few different ways. Sometimes it's easiest to write out the two separate equations, one for people with the dummy variable equal to 0, and the other equation for the people with the dummy variable equal to 1. Once we start with interactions, we just keep on going. What if we want delta wage, delta age to change both for different groups and for different ages? More interactions, of course. There's that beta 2 that we skipped before. Now we model wage equal to beta naught plus beta 1 age plus beta 2 age squared plus beta 3 d plus beta 4 age times d, that's the interaction of linear age, plus beta 5 age squared times d. That's the interaction term with the age squared term. The clearest view comes from rewriting those for the groups with different values of d. For the people with d equal to 0, we have the same age profile as before. For people with d equal to 1, now each of those coefficients might differ from the default group. In the graph, I've shown some possible profiles. There's a good deal of complexity in that picture. Does red or blue have a better wage-age profile? It depends. Blue starts lower, but gets higher and then comes down more sharply. Red starts higher, doesn't grow as fast, but also peaks later. It might be tough to see if you just stare at the equations. I don't know how much you remember your algebra class from long ago. Often it's helpful to draw the graph. From the equations for the two groups, people with d equal to 0, people in the base group, have a typical equation where wages are beta naught plus beta 1 age plus beta 2 age squared. For people in the other group with d equal to 1, the intercept term is beta naught plus beta 3. The coefficient on the linear term is beta 1 plus beta 4. And the coefficient on the squared term is beta 2 plus beta 5. Those additional terms might not be different from 0, and we have statistical tests to address how important that difference might be. With a little bit of calculus, oh joy, we can solve for where that y equals to 0 to find the maximum for each group. So for the group with delta equal to 1, delta wage, delta age is going to be parentheses, beta 1 plus beta 4, plus 2 times another parenthesis, beta 2 plus beta 5 multiplied by age. You can think of it as just taking those earlier two coefficients, beta 1, beta 2, and modifying each of them. Doesn't mandate the two groups have different profiles. They could be the same if beta 3, beta 4, beta 5 are all equal to 0. And we just talked about how to test restrictions on multiple regression coefficients to assess how strong is that restriction. Perhaps the two groups have very similar wage age profiles. Or perhaps they're different. We let the data tell us. We're not as interested in the individual coefficients. It would be weird to use information that beta 4 is, say, not different from 0 to conclude the model ought to restrict it to be exactly 0. That's not okay. You can't pick off a few selected coefficients of the polynomial. Do a joint test. One other way to look at these dummy variables is to imagine just doing two regressions on the two groups. For people with d equal to 1, do one regression. Then for people with d equal to 0, do a completely separate regression. That works. You get the same results and find these equations on the third line indeed hold valid. However, if you do dummy variables, then the statistical test is a little bit easier. Interactions of dummy variables are easy. Maybe the interaction is a little too easy sometimes. In R, you do a linear model of y is x plus d plus x colon d. That colon there is telling R to include all the interactions of the variables. An even shorter notation is just x star d. It will estimate the separate individual coefficients plus all of the interactions. That can be efficient when you know what you're doing, but sometimes be a little crazy making if you're left wondering, where did all that output come from? In the data sets that we're using, sometimes you need to tell R to treat certain variables as factors. That will create the dummies that are needed, and then you can interact them together to your heart's content. Other questions might arise. Can I interact dummy variables with each other? Yes, you can keep interacting and interacting and interacting. You can interact dummy variables for occupation with dummies for gender with dummies for education. It could be, for instance, a college-educated woman in the public sector who's a teacher is going to have a different wage-age profile. That's a plausible hypothesis. Might be difficult to estimate. There's absolutely an issue with sample size. Dummy coefficient estimates are based on means of subgroups. To estimate industry, occupation, gender, and education dummies, must look at what is the average wage of each of those interactions. People in a particular industry, particular occupation with a particular gender and a particular educational qualification, what is their average wage compared with people in the next industry or the next occupation or next gender or next education? We're cutting into smaller and smaller subgroups, which means larger error values. There may not be too many people in the farm industry in New York with an advanced degree. There's some, but not necessarily enough to get a precise estimate of what are their wage outcomes in general. And I'll close with a teaser that multi-level models, which we'll cover later, can really help. Finally, a sidebar on how the government creates industry or occupation dummy variables, or others too. Usually these are multi-level codes where more digits drill further and further down into more detail. There are similar coding schemes used for products and production and trade statistics. Look at industry dummies. The first digit gives a very broad categorization. 0 is farms and mines. 1 is manufacturers of non-durables. 2 is durable manufacturers. 3 is high-tech. 4 is transportation. 5, wholesale. 6, retail. 7, fire. That's finance, insurance, real estate. 8, services. 9, government. So if you have a 2-digit code, then the second digit adds more detail to the first level. Then 3 digits and 4 digits and 5 digits and so on. Some of these go very deep. It can be complicated as you look over longer time since the size of these industries or the composition might change dramatically.